and gentlemen, it's my pleasure to welcome you to our lecture series, AI in Science and Engineering of TU Wien. We have several internationally renowned and esteemed colleagues whom we could kind of invite and who accepted our invitation. And I'm very grateful that we start today with Professor Edith Elkind. Edith Elkind was professor of computer science at the University of Oxford before she moved to Northwestern University. She's really one of the figures and names in the area of computational social choice. And when I look in the audience, this is a topic which is also very well researched at TU Wien, and I see here a lot of faces who are, I think, very happy to have Edith Elkind here. She will give today a presentation about, you see the title, Multiwinner Voting, and for those who, and you are all computer scientists affine, I know, computer science affine, but if there are any people perhaps watching us and say, what is computational social choice, is kind of to model how you act and how you interact and how you decide in a social setting. And this almost sounds spooky, but it is not. There are mathematical models behind. And as I said, Edith Elkind is one of the most renowned scientists in this area. We are very happy to have you here, and without further ado, I would like to ask to give your presentation. Thank you.
Thanks, Professor Kappel, for a very kind introduction, and thanks for the invitation. It's a pleasure to be here. So as was mentioned, so I recently moved to Northwestern. So the background here is a beach cycling distance from my home, which is something that Oxford doesn't have, right? So that was part of the motivation. Okay, so I'll start my talk by talking about a very practical application of multiwinner voting that I think all of you can on board with, right? And as we move through the talk, we'll talk about less story, larger scale applications, and we'll end with an application to actual large language models, right? So eventually we'll get to what people normally these days understand as AI, right? But we'll start with something that would be traditionally thought of as social choice. Okay, so let's start. So suppose you are organizing a small workshop. So in fact, I know there's a person in the audience who organized a workshop recently here at TU Wien, right? So imagine you're organizing a 3-day workshop, right? And it's an interdisciplinary workshop at the intersection of machine learning and social choice, right? And such workshops do indeed happen. And suppose you, as a program chair, want to run this workshop democratically, right? And in particular, this means that you're going to select your invited speakers by asking your program committee members to vote, right? It's a small workshop. You have a small program committee, 9 people, right? And of those 9 people, okay, you've got 5 proposed speakers, and it's a 3-day workshop, so you have 3 slots for invited talks, right? So of your 9 PC members, there are 6 PC members who mostly work in machine learning and 3 PC members who mostly work in social choice, right? And there are 3 speakers. Kind of the way to read this table is rows are speakers, columns are PC members, right? And the way to read this table is there is a dot if a program committee member wants to see a talk by that speaker. Right, so you can see that there are 3 speakers who mostly appeal to machine learning researchers and 2 speakers who mostly appeal to social choice researchers. Right, so it's not black and white, right? So there's some cross-disciplinary appeal, but broadly the picture is like that. So my question to you, the audience, is in this case, do you think there should be a social choice speaker at the workshop? Can I have a show of hands? How many people would be in favor of having a social choice speaker? Okay, and you're not just saying that because you're a social choice person, right? Or because I'm a social choice person, right? You're not saying, you're not kind of supporting that to please me. Okay, so I would argue that there is a kind of very strong fairness intuition as to why there should be a social choice speaker in this conference, right? And what we will do now is we'll try to formally capture this intuition. So the formal model I'm going to work with is voting with approval ballots, right? So this is a very simple kind of voting where for each candidate, each voter says whether they approve it or not. So we have a finite set of alternatives, we have a finite set of voters, and each voter approves a subset of candidates, right? So saying, okay, so in case of invited speakers, so this would be invited speakers whose talk I want to hear. Right, and the goal is to select K winners. So K may be one, right? So when we are selecting a president or some kind of leadership position, but K can be more than one. And in this talk, I'm mostly going to be focusing on the case when K is more than one, because this is where things get interesting, right? And K more than one also makes sense. For instance, in the invited speakers application, we had K equals 3. So I'm going to illustrate some of the ideas by means of these kind of diagrams where I have dots for voters and ovals for candidates, right? In the intuition here that kind of if a voter approves a candidate, then this candidate represents or covers the voters, right? And we want to think of our problem selecting a representative committee as covering voters with candidates, right? So potentially covering them multiple times, but kind of set cover intuition will prove to be useful, right? So to explain the notation a little bit more, so here you can see oval C1 corresponding to candidate C1, covering dots 1 and 4, right? And that means that voters 1 and 4 approve candidate 1, as you can see, indeed they do. Okay, so that's the visualization, right? And this is kind of to connect what we are talking about to set cover. Okay, so if you have approval ballots, what's the most natural thing you can do with approval ballots? Well, you can count them. Counting approval ballots, it's what's known as approval voting, right? So that's by no means the only thing you can do with approval ballots. So maybe the name is slightly misleading, but this is what is usually called approval voting. So under approval voting, each candidate gets 1 point from each voter who approves her, and we select K candidates with the highest score, largest number of approvals. Right, so for instance here, if our job is select 2 candidates, so we'll count approval, C1 and C2 are approved by 5 voters, C3 is approved by 4 voters, so C1 and C2 are going to get selected. Right, and in particular, if we use approval voting, in this case, right, so remember we want to select 3 speakers, who are we going to select? Well, the first 3 rows have 5 dots in them. The second 2 rows have 3 and 4 dots respectively. So if we do approval voting, we are not going to select a social choice speaker, right? So we are going to select the first 3 speakers. And you can see how this is perhaps unfair and again, doesn't capture intuition that there should be a social choice speaker. Okay, so what's happening here? Why is there kind of no social choice speaker is selected? What is the property of approval voting that kind of prevents us from selecting social choice speaker? Well, going back to this picture, so what do we have here? Well, we have 5 voters who get 3 Okay, so there's a typo on the slide. So I revised this slide a little bit to simplify it. So my K is 2. So 5 voters get 2 representatives, not 3, 2. And 4 voters get 0 representatives. Right, and this is unfair. Right, so the reason this is unfair is imagine we scale this picture a little bit. Right, so instead of 5 and 4, we have 500 and 499, say. Right, and in that case still, 500 voters will get both representatives, 499 voters will get 0 representatives, even though the groups are almost equal in size. So what's the intuition here? Well, we have K slots, right? We are appointing K people, we are selecting K candidates. We've got N voters. So it seems reasonable that if you have a group of size N over K, right, so that group is large enough to deserve a representative. So if you have a group of size N over K that is cohesive, in the sense that it has coherent preferences, agrees on something, then perhaps that group should be represented. Right, and as we can see, this is something that isn't happening here. Okay, so let's formalize that. So this is a formal axiom that we came up with in a paper from roughly 10 years ago. So the conference version was in IIII, the journal version was in Social Choice and Welfare, a social choice journal. So we called it justified representation. Right, so this is the list of authors here. So it's Harry Sazes, Marcus Brill, Vince Konitzer, myself, Rupert Feynman, and Toby Walsh. We tried to get Toby Walsh to change his last name to Dalsh so that we could have ABCDF. We failed. Right, but okay, so this is the justified representation notion. Okay, so I have okay, so this is, Okay, slightly unpleasant to look at definition. So let me first say in words what I mean, right? And then we can look at the formula. Okay, so the bad situation I want to avoid is the kind of bad situation we had with our workshop. When we had a group of voters that is large, cohesive, and remains completely unrepresented. Okay, so let's see what that means. Large, we agree that large means having size at least n over k, large enough to deserve a representative. Cohesive means that they agree on some candidate, right? They can put forward a coherent proposal, like I want to see this speaker. And unrepresented means that the committee contains no candidate approved by any member of that group, right? And this is the bad situation, right? And we say that the committee provides that justified representation if this bad situation doesn't happen. So formally, a committee provides justified representation for n voters with ballots A1, AN, and a given committee size k, right? If there is no set of voters x, such that x is at least n over k, large, intersection of their ballots is non-empty, cohesive, such that the committee contains no candidate from the union of their ballots. Voters are unrepresented. Right, and as we can see from this example, approval voting fails justified representation. So here we have n equals to 9, k equals to 2, so n over k is n over k is 4 over 4, is 9 n over k is 9 over 2, 4.5. Okay, so did I mess up my numbers? Okay, so if I go back perhaps to this example, so here I can see easily that approval voting fails justified representation, right? So here I have nine voters, 3 slots, so 9 over 3 is 3. So if I have a cohesive group of size 3, then that group deserves representation. And I can see indeed that my last 3 PC members agree on the last speaker, yet under approval voting they would be unrepresented, right? So approval voting fails justified representation. Right, so my next question is then, okay, so approval voting fails it. Is there something more intelligent I can do with approval ballots to get justified representation guaranteed? Turns out the answer is indeed yes, and I'm going to give you not one, but 2 voting rules that satisfy justified representation. Right, and the first voting rule is what I'm going to call, for now, greedy approval voting. So greedy approval voting sort of leans heavily into this idea that when we do kind of voting with approval ballots, we are kind of doing set cover. We are trying to represent, we are trying to cover voters by candidates. Right, so greedy approval voting simply says, okay, let's do it greedily. We'll do it in k steps. So at each step, we'll select a candidate that covers as many uncovered voters as possible. Right, so we look at voters who are currently unrepresented in the committee, right, and select a candidate that is approved by many of these voters as possible. Right, and the claim is that great approval voting actually succeeds in providing justified representation. The committee outputs always provides JR. Right, so for those of you who are familiar with set cover algorithms, it's probably an easy exercise to see why this is the case. Right, so I can give you a hint. So the proof goes by contradiction, right? I mean, it's not a hard proof, right? So suppose we feel justified representation, then we've got this large, cohesive, unrepresented group. There's a candidate they approve, right? So that candidate, if we were to add it, would represent K voters, right? And we never selected that candidate because we've agreed. At each point, we were choosing something that was at least as good, covering K candidates, right? And if we did that, covering N over K candidate, N over K voters, and if we did that for K steps, we would have covered everyone. Okay, so that was a bit fast, right? So this is mostly to confirm the intuition for those of you who have seen something similar, right? So if you haven't seen it, I don't expect you to make sense of what I just said on the fly, right? But it's not a hard proof, right? And okay, so that gives us immediately a voting rule that provides justified representation. Okay, this is one. I promised you 2 rules, so here's the second one. So the second one is known as proportional approval voting, right? And that's a voting rule that has an interesting history. It was proposed by Danish polymath Torvald Thiele in early 20th century, and Thiele proposed it with the actual goal of selecting parliaments. Right, so selecting a parliament, right, like the entire parliament, not a single parliamentary member of parliament, but the entire parliament, is like a paradigmatic multiwinner voting problem, right? So we are selecting all of our representatives at once, right? And Thiele had this idea that we should be doing that not district by district, but at the level of the country. Okay, so this is how his proposal went. So suppose we are selecting a committee on the basis of approval ballots. So how are you going to feel about that committee? Well, certainly you're going to be unhappy if you don't approve anyone in the committee. Right? In that case, your utility from that committee is very obviously zero. Now, suppose you have one representative. There's one person you like in the committee. Right, so that makes you obviously much happier. So let's normalize it and say that your utility from having one representative is one. So what about the second representative? Right, it's certainly nicer to be represented by two candidates than by one. Right, but maybe having the second representative is not quite as important as having the first representative. So you derive additional utility, right, but maybe your additional utility is not one. So Tila said, okay, so let's assume that each voter from utility from having the second representative is one half. So your utility from having two representatives is one plus one half. Right, so diminishing marginal returns. And your utility from having three representatives is one plus one half plus one third. Right, and at this point, these numbers may feel arbitrary. Right, and Thiele didn't make a claim that these are actual utilities, but rather that this is a way of, accounting, assigning scores to committees. Right, so in this way, each voter assigns the score to a committee, right, and this is just the Tth harmonic number if the voter approves T committee members, right, and then we sum up the score of we sum up these utilities, right. So the goal is to select the size K committee that maximize the so-called imputed utilities. Right, so to illustrate, so suppose we have again this setting, right, where we argued approval voting for two candidates output C1 and C2, and let's see what proportional approval voting is going to do. Well, you still have the option of selecting C1, C2, right, and that will give 5 voters 2 candidates each, and 4 voters 0 candidates each. Right, so for these 5 guys, their utility is going to be 1.5, 1 plus 1 half, right, 1.5 times 5, 7.5. Right, so the PAV score of the committee C1, C2 is 7.5. So what if you were to select C1, C3? Well, then you have 9 voters who get utility 1 each. Right, so the overall utility is 9. Right, so this is better. Right, so C1, C2 has higher utilities than C1, C1, C3 has higher utility than C1, C2. C1, C3 is obviously tied with C2, C3. You can pick arbitrarily. But the point is that approval voting will do this imbalance thing where it will favor the slightly bigger group of voters, whereas proportional approval voting in that case will give representation to both groups. Right? And in fact, the claim is that proportional approval voting, not just on this instance, but universally, satisfies justified representation. Okay, so the proof of this theorem is slightly more complicated than the proof for greedy approval rule, so I'm not going to give you the proof, but let me still give you a high-level proof idea because this is going to be useful for what follows later. So suppose, okay, so here in this picture, here's my committee W, right, and C is the set of all candidates, and I'm going to proceed by contradiction. Right, so suppose my committee W fails proportional approval voting. What does it mean? It means that there's a large cohesive group that is not satisfied, right? And this large cohesive group approves, right? Because they're cohesive, they jointly approve some candidate who is not in the committee, right? So there's some candidate C sitting outside of the committee who is approved by N over K voters, right? And these voters don't like anyone in the current committee, right? So this is what it means to have a JR violation. Okay, so suppose we could magically extend our committee by 1 seat, just add 1 extra seat to the committee, right? And we could put C in that seat. How much would that increase the PAV score? Well, at least N over K, right? Because we've got this N over K voters, at least N over K voters who are currently at 0, and with that guy they would be at 1. So we've got N over K extra. Well, we can't get an extra seat on the committee, right? So the parliament size is fixed, right? So we've got 3 slots for invited speakers. We don't get to have a 4th slot. So if we were to add that guy C, we have to kick someone out, right? And now what remains to prove is that there is someone currently in the committee who is less useful than this outsider, that we can find someone in the committee to kick out, right? And the way this argument goes is by saying, okay, so if this committee W fails justified representation, right, so then kind of if you look at the marginal contributions of candidate in W, someone's marginal contribution has to be less than N over K. Right, and proving that is like a 2-line derivation, which I'm going to skip, right? But this is, again, not a very difficult proof. But kind of to summarize, kind of the proof here is a swapping argument, right? So if JR is violated, then there's someone outside of the committee and someone inside the committee, such that you can swap them and increase the PAV score. right? And that's a contradiction because we chose the committee that maximizes the PAV score. Right, so in other words, if JR is violated, right, so then there's a simple witness, simple swap kind of that allows you to increase the PAV score. Okay, so we started out by saying that here is a property that we want to have, and approval voting doesn't give us that, right? So we need a new voting rule, right? And indeed, I gave you two voting rules, not just one, I gave you two voting rules. I gave you greedy approval voting, I gave you proportional approval voting. So are we done? So maybe we're a little bit too early in the talk to believe that we are done. Okay, so what's the catch? Well, two questions you can ask. Okay, so first, so far, this was purely social choice, right? And I'm still a computer scientist. I mean, so AI now by trade, right? But theoretical computer scientist by training. So as a computer scientist, theoretical computer scientist, I want to ask, are both of these rules acceptable from a computational perspective? Do they admit fast algorithms to compute them? And second, is GR quite the right axiom to capture the intuition we had at the outset? Right, so the question is, okay, so the question to rephrase is, have we fully solved the notion of fair representation by either of these voting rules? Right, and there are two flavors kind of to this question. First, axiomatically, is justified representation the right axiom or not? Right, and second, algorithmically, kind of, are our voting rules computationally acceptable? Right, so let me now stay for now with the social choice flavor and talk first about axioms, right, and then talk about algorithms. Okay, so axioms. Right, so we said that JR is kind of our, first approximation to the notion of proportionality. If you have a group that deserves one slot on the committee, right, by virtue of being large and cohesive, right, then that group should be represented. Well, suppose though, right, and I mean, this is far as fine as it goes, but suppose you have this situation. You're selecting two winners, your committee size is 2, right, and you have a very large group on the left, right, so I was lazy, so I only drew 13 points, right, but imagine this is like 1300, right, and they all approve candidate C1, and C1, C2, C3, right, and there's another group, there's candidate C4, who is literally supported by two voters, right, which is candidate C4 and their partner, right? So we've got a group of 1300 on the left, and we've got two people on the right. Under these circumstances, what does JR tell us? Well, JR tells us is that we absolutely have to choose one of C1, C2, C3, right? But it also allows us to choose C4, right? So it says that the committee C1, C4 is perfectly legitimate, right? Because it gives the group on the left representation. Right, and I'm not sure that this is exactly fair, right? I mean, so it's kind of nice that everyone in this circumstance gets represented, right? But maybe if C4 really is only supported by themselves and their partner, right? So maybe we should rather give more representation to the very large group on the left, right? So maybe if we have a very large coherent group, maybe they deserve several representatives. Okay, so how can we conceptualize that? Well, so the idea of justified representation is that if you have a group of size n over k, it deserves one representative. Right, so now let's scale it up. Suppose that if we have a group that is at least L times n over k and also agree on L candidates. Right, so let's scale up both the size condition and the cohesiveness condition. So if that holds, perhaps they deserve L representatives. Right, and this is the axiom that we're going to run with. So this is something that we also introduced in the same paper, and we call it extended justified representation. Right, so this is written not in math but in words, but kind of this is roughly what I just explained. If we have a group, if we have a set of voters that is L large and L cohesive, then we require the committee to contain L voters approved by at least one member of that group. Okay, so though kind of one can complain that this condition, at least one voter receives L representatives, is slightly weird and maybe doesn't quite capture intuition, right? And that slightly different ways of phrasing that. So for instance, there's a slightly different definition saying, okay, there should be L members of the committee approved by at least one member of group X, right? So this is a slightly different axiom, weaker than this one, right? But okay, this one also kind of gets to the idea that if a group is L large and L cohesive, it should get L representatives. Okay, so as you expect for L equals 1, it boils down to justified representation, right? But it's a strong axiom because, I mean, it also has a bite for larger value of L, right? So Okay, so some people here may be wondering, kind of, if there's anyone here with a strong game theory background, there's a concept of core stability. So this is related but not equivalent to core stability. So let me not get into more details here. Right, and now the question I want to ask, okay, so here now we have our strong axiom, right? And we have two voting rules that we argued are good. Greedy approval voting and proportional approval voting. Are they still good if we evaluate them according to this axiom? Okay, greedy approval voting versus proportional approval voting. Are they going to give us extended justified representation? We know they give us justified representation, but how about extended justified representation? Well, let's start with greedy, right? And immediately I have bad news for you. Greedy approval voting fails justified representation. Right, I could give you a concrete example, right? But let me just wave my hands around it and say that once a voter is represented, greedy is no longer interested in covering it, right? It's been covered, it's been sort of removed from the picture, so greedy will not try to cover it for the second time. Fundamentally, greedy is in the business of covering each voter once. Once a voter is covered, it ignores it, right? And extended justified representation may require us to give several representatives to a voter, right? So greedy approval voting is not going to do that, right? So instead it will find, candidates approved by, so far unrepresented voters, right? Even if the candidates have very few approvals, right? And select those candidates, right? So greedy is not going to give us that. On the other hand, right, and this is slightly more complicated proof again, like maybe 3 lines of derivations, proportional approval voting satisfies EJR. So for EJR, I told you that this is a swapping argument. There's someone outside of the committee and there's someone in the committee, such that if JR is violated, you can improve the PAV score, right? So the same argument kind of works for EJR. So again, a local swap argument. So now we have a way to distinguish between our voting rules, right? So we have great approval voting that only gives us JR, right? And we have proportional approval voting that gives us EJR. So it seems like we have a winner. But now let me put on my computer scientist hat, right? And let's now talk about the computational complexity of these voting rules. Greedy approval voting is doing wonderfully, right? It's very easy to run the greedy algorithm. At each step, you look at each candidate, you see how many voters who so far don't approve anyone approve that candidate, and we can add that candidate to the committee, right? So that's certainly efficient. So what about proportional approval voting? Well, I gave you something that feels like an efficient algorithm, right? But that was an algorithm for evaluating a given committee. I told us that if you have a committee, here is how each voter evaluates that committee, right? And here's how we can compute the score of that committee. And then I said, okay, and now we're going to select a committee with the maximum score. I didn't tell you how to actually find that committee, right? And from what I said, it sounds like, okay, you can go over all committees, compute the score of each committee, select the best one. And of course, this is computationally expensive. Can you do better? Well, not really, not much better unless P equals NP. Proportional approval voting is known to be NP hard to evaluate. Okay, so when it comes to complexity, again, we have a winner, except now the winner is greedy approval voting. So we have, okay, 5 minutes ago, we had 2 good voting rules, both satisfied JR. Now we are back to having 0 good voting rules, right? Because one voting rule is good axiomatically, but not computationally, PAV. The other voting rule is good computationally, but not axiomatically, greedy approval voting. So can we have the best of both worlds? Right, and this is the question we asked at the conclusion of our 2015 paper. Is there an easy to compute voting rule that satisfies extended justified representation? Right, and that sort of generated a line of work. And okay, so some of that was in the original paper and some of that was in follow-on papers. So let me walk you through some of that. Okay, the first attempt was to try and fix greedy, right? Because proportional approval voting kind of seemed like, okay, fundamentally an NP hard voting rule, right? And then our idea was, okay, so greedy approval voting, maybe it doesn't give us EJR, but at least it gives us JR, and it's easy to compute, right? So maybe we can tweak it a little bit. Okay. So this is, okay, sorry, let me take it back. Okay, let me tell the story slightly differently. Okay, let's go back to the ideas of Thiele. Right, so remember Thiele wanted to use PAV to select parliaments. Now parliaments, right? So even at the beginning of 20th century, so he was Danish, but he was actually working on he wanted to have his voting rule used to select the parliament in Sweden, right? Even at the beginning of 20th century, Sweden was a sizable country. with a sizable parliament. So he actually had to think about the efficiency of his voting rule, computational efficiency. Now, the notion of NP hardness wasn't around back then, early 20th century, right? So the notion of NP hardness is roughly as old as I am. So it wasn't there when Thiele was doing his work, right? So he couldn't formally say the PAV rule as I proposed it is computationally hard, right? I mean, so what he really wanted was an approximation algorithm. He didn't have a notion of approximation algorithm either, right? So that theory came later, right? But he could still say, okay, we want something that is kind of quick and dirty and efficiently computable. So let's try a heuristic. And heuristic he proposed was a sequential version of the PAV rule, right? So the sequential version proceeds kind of like the Grady algorithm, but instead of operating with coverage, it operates with PAV scores. So again, it proceeds in k rounds, and at each round, it adds a candidate that increases the PAV score as much as possible. Right? So at each point, you try to maximize the PAV score locally, but not globally. Right? So to show you how this is different, let's look at this picture. So suppose you're in the business of selecting a committee of size 2. Right, obviously with respect to PAV score, the best thing you can do is to select C2 and C3, right? Because this way you'll cover all candidates and your PAV score is going to be 10. But if you're doing greedy PAV, right, at the first step, it will try to cover as many candidates as possible at that first step. So it will take this cross-cutting candidate C1, right? And then it won't be able to go back. It will have to choose C1 or C2. It will have to add C2 or C3, right? And that will fail to maximize the PAV score, right? So greedy version of PAV is distinct from PAV, right? But it still preserves some of the PAV flavor, right? And that, in fact, was briefly used in Sweden, right? So the question we can ask now is whether the sequential version of PAV kind of gives us EJ. Turns out that if you do just that, this is polynomial time, but it fails not just EJR, but it actually fails JR. Okay, so this idea didn't work. Kind of taking PAV and transforming it into a greedy heuristic didn't quite work. Okay, so we tried that, right? And here was our next idea, right? So I told you that Thiele defined PAV with the sequence of weights 1, 1/2, 1/3, right? And I almost expected someone to complain, like, why these numbers, right? So why harmonic sequence? I mean, harmonic sequence is a nice sequence, right? But why not take like exponentially declining weights, 1, 1/2, 1/4, 1/8, or kind of some other sequence of weights? So why harmonic weights, right? So our next hope was that maybe if we tweak the sequence of weights, if we go with smaller, faster declining or slower declining weights, maybe then we can restore EJR. Right? Okay, so how do we define it formally? So PAV and sequential PAV, they both use harmonic weight vector. How about we use an arbitrary weight vector? Okay, so what does arbitrary mean? We want the scores to, go down, right? So we certainly don't want them to be non-monotone, right? So I mean, potentially kind of, stay flat for a while, then go down. Right, and we'll normalize the first score to be 1, right? So kind of just to have all these vectors comparable, right? But we can potentially use any weight vector that satisfies this condition. The first weight is 1, and then weights are declining, right? And we can use that as an optimization objective or as a greedy version, right? So each such vector defines a score, how you evaluate a committee, right? So you evaluate kind of each voter assigns a score of W1 plus W2 plus WS to a committee where he approves S people, right? And we could try to globally maximize the score, or we can add candidates one by one, maximizing the score at each step, right? So both options are feasible, right? So in fact, if we try to do that with scores 1, 0, 0, 0, so what does that mean? Right, so it means that each voter evaluates a committee kind of based on whether this committee contains one candidate they approve, right? If there's one candidate they approve, they give that committee a score of 1, right? Having more candidates doesn't help, right? So the second coordinate onwards is 0. But like if committee contains one candidate you approve, you give it a score of 1. Otherwise, you give it a score of 0, right? And this is basically set cover, right? Or maximum coverage. You're trying to select a set of candidates that covers as many voters as possible, right? And the sequential version of that is a voting rule we've already seen, Right, so this is greedy approval voting. Right, so at each point, we add a candidate that covers as many additional voters as possible. Right, so we now see that kind of proportional approval voting and greedy approval voting are kind of members of the same family. One sequential, the other non-sequential, different weight vectors, but they're sort of part of the same framework. Okay, so this framework actually is useful in that it captures both rules we have seen, right? And now the question is, can we play with weights and get extended justified representation? Right, and I mean, so we already have some good news, right? So we know that if we do the sequential version of this rule with vector 1, 0, 0, right, we satisfy JR. Right, so I told you that we don't get JR if we do the harmonic weight vector, but with 1, 0, 0, 0, we get JR. Right, and maybe with some other weight vector, we get even more. Okay, we also know that greedy fails EJR, so that weight vector won't do. We need a different weight vector. Right, and here came our first surprising negative result. The negative result says that if you depart at all from the weight vector 1, 0, 0, 0, if you choose weights that are, basically departing from that means having second weight as strictly positive, right? Because it has to decline, right? So if it's different from 1, 0, 0, 0, so the second weight has to be positive. And as soon as you have that, you break JR. Right, so our goal was to have the strong axiom, EGR, but it turns out that the construction is very fragile. If you start tweaking it, you lose even JR you had to start with. Right, so that research agenda didn't work, right? So you really, if you do things sequentially, you really have to have 1, 0, 0, 0. Right, so now just out of curiosity, so suppose now we're giving up on computational complexity, but we want to know how robust is our result for PAV. So we said that PAV satisfies EGR and has this harmonic weight vector. Are there other weight vectors that give us EGR? Turns out the answer is no. Turns out that the harmonic weight vector wasn't there randomly, wasn't there arbitrarily. Thiele somehow guessed it, right? So there's a longer story how he guessed it, wasn't completely out of the blue, but it was still surprising that he got it. You really have to have harmonic weight vector to get EJR. Any other weight vector, you are not going to get it, right? You may have JR, like weaker version of the axiom, but if you want EJR, you absolutely have to have harmonic weight vector. Okay, so we got something out of this approach. We got an explanation for the harmonic weight vector being there, but it still doesn't give us an efficient algorithm. So if our plan is to get something that satisfies EJR and is efficiently computable, here's another algorithmic technique we can try, right? And this is local search. Okay, so the local search algorithm is based on the following observation. If a committee fails EJR, right, so our proofs, if it fails EJR, then there's a local swap. We can take a candidate outside of the committee and candidate in the committee, swap them around, and get a committee with a better EJR score, with a better PAV score. Right, that actually gives us an algorithm. Right, and the algorithm tells us the following. Right, so we can start with an arbitrary committee, right, and check for local swaps. Check if there's a candidate in the committee and the candidate outside of the committee, such that if we swap them, the score increases. Right, and kind of by our proof, if there is no local swap, then EJR is satisfied, right? Because we argue that if EJR is failed, there is a local swap. So contrapositive, if there is no local swap, if we converge, EJR is satisfied. Right? This seems like a reasonable algorithm to implement in practice. Start with an arbitrary committee, perform local swaps. Each local swap is easy to implement polynomial time. What is the step that I'm missing now? How many swaps? Right? Each swap is easy to identify and implement. It's not at all obvious that the number of swaps is going to be polynomial, right? Because each swap is going to increase the PAV score, but maybe it will increase it by a tiny little amount, right? So a priori, it's not clear if this algorithm converges in polynomial time, right? So this is something that you may want to try in practice, but it's not clear how fast the convergence is going to be. So it gives us EJR. Each iteration is easy to compute, right? But in fact, right, so that was the algorithm from the original paper, 2018, where we sort of made the observation that we don't know how to show polynomial time convergence. And in a subsequent paper with my student Sonia Krejci, Sonia showed, and I helped her write it up, right, that the number of iterations may in fact be super polynomial, right? So this may be practical, right? This is a useful heuristic, right? But it's not an actual polynomial time algorithm. So we need one more step. So what is this step? So again, looking at our proof, so our proof said that if a committee fails EGR, we can find a committee with a better PAV score by local swap. Okay, if you look at this proof more closely, it doesn't just give you better, it gives you much better, right? And much better means quantitatively at least n over k squared, right? So if a committee fails EGR, you can perform a swap and increase the PAV score by at least n over k squared. Okay, and this is actually what we need, right? Because what is the maximum possible PAV score? Well, you've got n voters. Each voter score for a committee is at most the kth harmonic number, 1 plus whatever 1 over k, so roughly log k, right? So the maximum score is polynomially bounded, right? It starts at least 0. It starts at a non-negative amount. If we improve it by at least that much at each step, right, we are bound to have polynomially many steps, right? And that gives us an epsilon version of our algorithm. Start with some committee, and if there is a local swap that improves the PAV score by at least epsilon, perform it, right? And stop when there is no significant improvement. And kind of what this argument says is that if we take epsilon large enough, then we'll have polynomial time convergence. And if we take epsilon small enough, at most n over k squared, we'll have EGR, right? So in particular, if we take epsilon equal to n over k squared, right? So then the resulting rule satisfies EGR and is polynomial time computable, right? So at this point, we managed to restore polynomial time computation and satisfaction of the EGR axiom. So we were very proud at that step. We were very proud at that point. But, okay, so this is my voting rule. I started with an arbitrary committee. I perform local swaps one by one, right, until there is no local swap that improves the PAV score by more than n over squared. Is this the kind of voting rule you want to explain to members of your family who are not computer scientists? Okay, maybe, computing PAV score, maybe, right? I mean, it's kind of complicated, but fundamentally this is just arithmetics, right? So you can explain this idea that we're computing committee scores, we select the committee with the best score. The idea of local search, okay, more dubious, but maybe. The idea of epsilon local search, when you leave on the table small improvements because you care about polynomial time computability, okay, no, hard no. That you're not going to explain to, layman audience, right? So this is a proof of concept. This isn't a usable voting rule, right? So polynomial time computable, right, and satisfying a nice axiom doesn't quite capture it, right? So if we actually want to have EGR in practice, we need something else. Okay, so, and this something else was actually achieved by a team. So I take partial responsibility for that, right? So this was achieved so I'm not a co-author on this paper, but it was proposed by people who used to work in my lab, right? So that's Piotr Skoven and Dominic Peters. Piotr was at that point my former postdoc. Dominic was my PhD student. And they proposed a voting rule that they call method of equal shares, right? And method of equal shares very briefly works as follows, right? So it starts by giving each voter a budget of, okay, so that's a typo again. So a budget of k over n, so that the overall budget is k, right? And then the voters, iteratively voters form groups to buy candidates they jointly approve and share the cost equally, right? So at each point for each candidate, we say, okay, so if we were to buy this candidate, which voters who support that candidate still have money, right? The caveat is they have to share the cost of that candidate equally. And okay, and we buy at each point the candidate with the smallest cost, right? So I'm not going to give you an example, right? But it's a fairly easy to make that concrete, right? And I think that's also an explainable voting rule, right? And the design of this voting rule was motivated by the desire to satisfy EGR, and indeed it satisfies EGR and is polynomial time computable, right? And it's actually a intuitive voting rule, right? And I have an argument for that, in favor of that is stronger than just, look at it, it seems easy to compute, right? But let me get back to that in a couple of slides, where I think method of equal shares is a wonderful voting rule, right? And let me maybe wrap up the, theory part of this talk and move on to applications. Okay, so that was the theory of justified representation and extended justified representation, right? So what else is there? Well, kind of the world of the zoo, I should say, of justified representation axioms doesn't end with EJR. So there's JR, there's EJR. There's notion of the core from cooperative game theory, of which EJR can be thought of as relaxation, right? So there's kind of notion of core stability, which is also an axiom in this family. Kind of there are other notions that end with JR. So there's full justified representation, proportional justified representation, kind of they come with the plus versions, you can combine P and F, right? So in the end, kind of what we started in that line of work, so JR and EJR, grew into a bit of cottage industry of representation axioms, right? So some were driven by trying to understand which flavor of justified representation is satisfied by this or that voting rule, right? Because some voting rules don't give you EJR, but they give you something slightly weaker but close, so still useful. So you want to know that, right? And some axioms are stronger, so you can achieve more fairness, right? And then it's interesting to ask, okay, can you achieve more fairness by existing voting rules, new voting rules, polynomial time, right? So this is still like a large and active research area. The last axiom on this list, FPJR, was introduced roughly a year ago, right? So this is still evolving. We still don't have a complete picture. Right. So with new axioms come also new voting rules, right? I mean, old voting rules which are now proven to have, properties from that list, but also new voting rules that were invented specifically to satisfy these properties. Right. So I highlight in blue things I have worked on personally, right? But there's much more out there. Right. Okay, so something you can also ask is price of justified representation, right? And this is the following question. Suppose you actually want to maximize something when selecting your candidates, right? You want to maximize the total satisfaction, right? So you want to maximize how many voters are represented, right? But at the same time, you want justified representation, which is a different flavor of property, right? It's not about representing as many voters as possible, right? It's not about representing the sum of satisfaction of each voter, right? It's something in between, right? It's a kind of group fairness axiom. So if you impose this group fairness axiom, what impact may it have on other desiderata you may have, right? And this is what's called price of justified representation. And by now we have a fairly good understanding of what this price of justified representation is for various desiderata. Something else I worked on is temporal voting, right? So this is when elections happen over multiple time periods. So the other people in this room who've done kind of more on that than I have, so Jan here, right? But kind of the idea here is that to look at elections that happen kind of repeatedly in multiple periods, right? And ask, so what is the correct notion of justified representation for multi-period voting over time, right? And we have some work in that space as well, right? The justified representation ideas can also be applied to the very practical domain of clustering, right? So when we're in the business of selecting K cluster centers to represent a set of endpoints, right? And I mean, typical clustering objectives are not quite like justified representation, right? But you can ask, so what if you were doing clustering with justified representation in mind? What kind of clustering algorithms would you want to use? What kind of guarantees do you get from standard algorithms, right? So that's an interesting question to ask. So this has been asked by people other than myself, but I have some ongoing work in that field. Okay, but this is kind of to show you how this led to, fairly rich and interesting theory. But now let me switch to applications. Right, so in the first application I want to talk about is the application to participatory budgeting. So the city of Vienna runs a participatory budgeting program, but I'm not sure how many of you are aware of that. So how many people know that there's something called participatory budgeting in Vienna? Okay. Roughly half of the people. Okay, so let me explain what participatory budgeting is. So maybe you know the term in German, but not in English. Okay, so maybe you'll recognize when I talk about it. So there's a set of N projects, right? And these projects would typically be neighborhood improvement projects, right? So building a playground, improving the condition in the animal shelter, investing into training firefighters, opening a community garden, right? And these are all examples of projects that occur in real life. So in Vienna specifically, I think the focus is on projects for children that are proposed by children and are voted on by older children. Right, so maybe the playground and less of a community garden, but yeah, who knows? Right, so there's a set of project and there's a budget, right? And this is something that local municipalities run, right? I mean, not the whole budget of local municipalities typically allocated this way, but like a small fraction of it. For instance, in Scotland, the rule is like 1% of local municipality budgets have to be spent using participatory budgeting method. So there's a set of projects, there's a budget, and each project has a cost, right? So a community garden and training firefighters are not necessarily kind of on the same scale, right? So we are talking about projects that range from maybe hundreds of euros to, couple tens of thousands of euros, right? And budgets that could be on the order of 100,000 to million euros, dollars, kind of roughly that order of magnitude, right? So then voters are asked to vote to report their preference over this project. So those could be approval preference, so they could be more complicated ballots, right? So that again depends on municipality, right? And then a set of winning projects is selected, subject to the budget constraint, so budget B, right? And it's selected based on voters' preferences, right? So this seems like a nice thing to do. And in fact, it's been happening around the world for over 30 years. So it started in Brazil, in Porto Alegre in 89, right? And since then it's spread around the world, right? Including the city of Evanston, where Northwestern is located, and including Vienna, where it's used to select child-led projects. Okay, so how does that relate to what I've been talking about? Well, if you think about participatory budgeting, right, so this is just a fancier version of multi-winner voting, right? Or maybe in other words, you can think of multi-winner voting as participatory budgeting, where each project has the same cost, right? And the goal is to select K projects, right? So the general version is more flexible, right? So maybe you can select 10 cheap projects or 5 more expensive projects, right? But certainly if all projects have the same cost, it becomes the same as multi-winner voting, right? And it turns out that kind of all the work we did in the context of multi-winner voting kind of extends naturally to participatory budgeting setting. So the EGI axiom can be extended to the setting of participatory budgeting with approval ballots. And the method of equal shares, perhaps more importantly, also kind of extends naturally to participatory budgeting, right? And moreover, so both extend, right? But also the positive result extends. The method of equal shares satisfies EGI in the context of participatory budgeting, and method of equal shares have been used in practice. So I promise to try to convince you that method of equal shares is a voting rule you can actually explain to people, right? And there's a proof of that actually happening in practice. There are so far, I believe, 5 towns, all of them in Europe. The method of equal shares has been used for practical participatory budgeting applications, right? And I think kind of the reception of that was generally positive, right? And, kind of members of the community who were engaging with that, right? So these are kind of my various co-authors in kind of Poland, Dominic Peters, who is now in France, colleagues in Switzerland. So they all managed to convince local municipalities that method of equal shares is a good way of doing participatory budgeting. So the standard way so there are all these other places that do participatory budgeting. What do they typically do? They typically do some version of Gerti, right? So they order the projects by the number of votes, right? Or number of votes divided by cost or something like that and select in this order, right? And in these 5 places, kind of people from the community managed to convince the practitioners to use method of equal shares, right? And there are reasons to believe that this was successful, that the reception was generally positive, right? So most of these places are continuing with the method of equal shares. Those who aren't are not doing that because their method was bad, but rather because of other political changes. Okay, so that's the first application, and one I'm probably kind of most proud of, right? Because in a way, the method of equal shares grew out of a desire of satisfying the EGI axiom, right? And it went from purely theoretical concept to something that is used in practice, right? But let me tell you about applications other than participatory budgeting. So the next application I want to talk about is blockchain. So I imagine, so you can't help but I imagine everyone in this room have heard about kind of various blockchains, kind of Bitcoin being the most popular one, right? And I think many of us probably have heard by now about the distinction between proof of work versus proof of stake. Proof of work are the evil blockchain protocols that burn a lot of, electricity, right, to add blocks to the blockchain. Right, so blocks of verifiable transactions have to be added to the blockchain, right? And Bitcoin and many other blockchains do that by forcing verifiers kind of to solve difficult computational puzzles. So it takes a lot of electricity to build on the blockchain. There's another kind of blockchain which is called proof of stake, right? And the proof of stake blockchains, validators add transactions to the blockchain, right? And the system is based more on trust in kind of the honesty of validators. and kind of incentives for the validators than on burning electricity, right? So this is the less evil kind of blockchain, right? And in particular, one of those less evil blockchain, Polkadot, right, uses something that is motivated by this line of work. So let me tell you a little bit more about that. In proof of stake protocols, so new blocks are added to the blockchain by validators. So who are validators? Validators are stakeholders in the blockchain, token holders, right? So they have because they're token holders, right? So they have financial interest in the blockchain being run correctly, right? So they want the blockchain not to collapse, right? And on the other hand, potentially kind of by adding fraudulent transactions, they could benefit from it, right? So there's a trade-off. So what you want to do when selecting validators is to select validators that broadly represent your stakeholders in the blockchain, with the hope that because kind of you have this broad selection of validators, fraudulent transactions will not go through. Well, so this means that effectively, okay, token holders need to approve the validator candidates. So effectively, there's a multi-winner election for selecting the validator that is run each day, right? So a new committee of validators is selected daily, right? And the kind of research group behind this blockchain decided that something like justified representation, in fact, a slightly stronger version of it that we didn't talk about, proportional justified representation, is something that is going to prevent adding fraudulent transactions on their blockchain, right? So as a consequence, so to the best of my knowledge, it's still the case now. So the paper is from 5 years ago. Polkadot is a nominated proof of stake protocol that appoints validators using a rule that satisfies JR, right? And JR and related notions are indeed the motivation for using that voting rule. Okay, so that's application to blockchain, right? And kind of two more applications I want to talk about. So one is social media and then finally LLMs. So this is a recent paper by a research group from Meta, Facebook, right? So when we're interested in filtering the comments on social media, right? So the setup here is something like, imagine comments maybe on a Facebook post, right? Or maybe, a newspaper article where you have comments from the readers, right? So the very practical problem that these platforms have to solve is which comments to show first, right? And especially, okay, so what happens when you press most relevant when you want to see comments on an article? How does it select most relevant, right? So you certainly don't want to select, just comments that got the most votes because they may all focus on one point of view. You don't want to just show the most recent comments because maybe they're just boring comments that say, great, I agree, right? So you want to have a broad swath of comments. Right. So the model that they work with is we have a set of M comments on social media, right? And then there are users that come dynamically to the platform and they engage with the comments, right? So they may respond to a comment, they may press a like or an angry sign or something, depending on the format, right? But each comment gets some kind of engagement score, right? Which at some level of approximation you can think of as approval, right? And then your goal is to select a subset of K comments to highlight, right? So you're in the business of selecting K out of M, you are doing a multi-winner election, right? So the inputs are not quite as approval ballots, but at the same level, at some level, you can simplify it to approval ballots. So comments also have quality scores, right? So this can come from textual analysis, this can come from approvals, this can come from the type of likes they get, from the kind of engagement they get, right? So it's not as simple as selecting on the basis of approvals, right? But there's also quality. So what this group shows is they're experimenting with a Remesh platform, which is a platform where you can collect opinions on issues, right? So they don't experiment directly with Facebook, but I understand that eventually these ideas have been implemented within Facebook, right? And the key finding is that if you select the committee, if you select the K comments to show in a way that satisfies justified representation, then you don't lose much. You can do it in such a way that you don't lose much in the way of quality scores, but you actually improve representation of across political groups, across political spectrum, right? And in this way, you hopefully reduce polarization in the society, right? So you show to the readers of the news articles that there are different opinions out there, right? That we don't have monolithic culture saying this or that, right? That there is a range of opinions in the society. And building on this idea, so I now have a collaborative project with people, there's a large overlap with people listed on the previous slide, right? But also okay, also my student Sonia Kraichi, Ariel Prakacha, Emin Berker, right, and a bunch of people from Meta, where we try to take the same ideas and use them in application to LLM training, right? So our goal here is to get LLMs to give answers to controversial questions that are sort of not just black and white answers, but representative of the spectrum of the opinions in the community when there is a spectrum. Right, so more specifically, the task we're interested in is training large language models to answer socially contested prompts. Let me give you an example of something that is, controversial, but moderately controversial. So for instance, should police use facial recognition? Right, and I think this is this is the kind of topic that people can potentially ask LLM for advice, right? So what do you think? Should we kind of as a society proceed in this fashion or another? Right, but typically people don't have super strongly held opinions. Should we extend the presidential term? Again, opinions may vary. They may be opinions kind of in favor of yes, in favor of no, in favor of yes, but, right? So this is something that kind of is within the realm of reasonable discourse, right? And what we want to do is to make sure that kind of an LLM is asked a question like that, it sort of gives a spectrum of opinions, right? It says, okay, the arguments in favor of this, the arguments in favor of that, right? And there's something in between, but also that it doesn't give answers that are completely outside of, the realm of socially acceptable, right? So there's a concept of, Overton window, right? So the range of opinions that are seen as possible. So we want LLMs to cover the Overton window, but don't go beyond it, right? So the question is kind of, can we do that? And can the ideas of kind of along the lines of justified representation be useful? So we want to reflect viewpoints of sufficiently large groups, right? And there's like a JR style, proportionality style flavor right here, right? So the opinions that we want to have represented are opinions that are held by large cohesive groups, but maybe not by small fringe groups. So the way we approach it is as follows. So we start by recruiting a representative sample of human labelers, right? So this is kind of the expensive part. So you need collaborators such as Meta to do that, right? Because, that isn't something that academic researchers can afford to do, right? And then so we recruit this representative sample of human labelers, right? And we ask them a whole bunch of questions, right? And based on that, we train personalized LLMs that match each of our human labelers, right? And then for each response, we ask these LLMs, right? So we get a bunch of responses, right? And then from those, we select K representative responses, right? So we select a committee of responses using I want to say JR style techniques, right? But it works in the space of embeddings, right? So there's a Euclidean flavor to it, right? So this builds on some of the clustering ideas developed by the community building on JR ideas, right? And then we take these key responses and we use the LLM to merge them into a pluralistic output, right? And for now, this is still work in progress. The theory is more or less complete. We are planning to release it in archive soon, right? But the practical experiments are still going on. So we are past the recruitment stage and collecting responses. We're in the business of training personalized LLMs, right? And the interesting considerations how you actually do that, right? But our preliminary results are promising, right? It seems like this is a good way of generating balanced responses, right? And in some way, it's an improvement over what current language models do. Okay, so basically okay, so let me stop here and maybe just to summarize. So we started with a very simple application, selecting workshop speakers, right? And it helped us develop intuition for what it may mean to have a personality when you're selecting K alternatives on the basis of approval ballots, right? And that turned out to be a computationally challenging problem, but I think eventually we came out on top, right? And then it turned out that there's a whole lot of applications of these ideas that go way beyond our initial ideas, right? That range indeed from blockchain to large language models. Unfortunately, I don't have applications to quantum computing, right? To hit, all the hype areas, right? So maybe that's in the future or not. But I think this is actually exciting, right? And if it ends up making our world like a less polarized place, right? So I will be happy that my research found a way to contribute to that. Okay, let me stop here and I'm happy to take questions.
So thank you for your presentation, especially, make the world a less vulnerable place. I think it's a very, very good remark at the end. Questions from the audience?
Maybe I ask about this slide that's still here, because that work I obviously haven't read yet. So I'm very curious about the last step, because I think everything before, I can imagine how you do this in a theoretically sound way. But also, do you have some understanding whether merging K response with an LLM, I assume, keeps the representativeness, or if the LLM might, in the merging process, destroy the responsiveness? And can you even theorize about this or do this empirically?
I mean, yes. Okay. So very good question. Thanks. Right. So for now, so the way we've been doing it so far is mostly empirical. The way you can try to approximate it is to say that, the number of votes allocated to each position kind of captures its share of the committee, right? And then you may potentially want to work with different weights on the candidates as well, right? So there's room for developing theory there, and we're working on now, right? But for now, this step is is practical, right? And we are not sure how well it actually works. And yeah, I would be interested to discuss how you would evaluate the outputs. Right? Maybe there's theory to be developed around that. Thanks.
Like some examples, because it looked to me that a lot of problems came from the fact that a group of voters casted multiple votes, while a smaller group casted just one preference. Would the results change if we either force just one vote per voter, or if we force multiple selection of preferences for all voters?
Okay, so this, I think, so we interpret the vote slightly differently. So what you're referring to is that some voters approve multiple alternatives while other voters approve single alternative, right? So I think this is something that we, at some level, we don't want to force, right? So we want people to, if they're flexible and happy to be represented by several different candidates, we want them to be able to say so, right? Whereas if someone really just would be happy with just this one project, like think in the context of participatory budgeting, right? So if I would be happy by several projects being implemented, I should be able to say so. If I only like one project, I should be able to say so, right? I think preferences are intrinsically like that. Some people approve many things, some people approve few things, right? So if you sort of force people to specific ballot formats, right? So then maybe you'll get something, right? But what you will be getting will not be with respect to the true preferences. It will be with respect to the reported preferences, and the more structure you impose, the further away these reported preferences will be from true preferences, right? So you'll have to deal with strategic considerations. I mean, you already do with these voting rules, but to a larger extent, right? And simply, I think my philosophy is it would be good to have a ballot language in which people can express their preferences as close to their true beliefs as possible. So.
Thank you very much for the very interesting talk. Yes, I want to ask about the voting setting. So approval voting is obviously very simple. So everybody casts just say yes or no to his favorite candidates. What do you think about what if people want to have intensities, for instance, rankings? And so for single winner election, for instance, it's usually started under rankings, but here we have approval voting. So do you think that this kind of proportionality can be extended to ranking settings?
So there are two questions here. One is whether axioms can be extended, and the other one whether voting rules can be extended, right? And these are two separate questions, right? So for voting rules, so for instance, method of equal shares naturally extends to the setting when voters report the utilities for the candidates, right? Or some restricted forms of these utilities, right? So the axioms also can be extended in ways, so the theory becomes much less clean, but it can be extended both to rankings and utilities, right? So I have some disagreements with how it's been formalized so far. It's something that has been attempted, right, but becomes less clean. So I think the cleanest way to do that might be to say, okay, so if we have this ranked ballot or utility ballot, right? So there are multiple ways to convert it to approval ballots, and for each way of converting it to approval ballots, we want these properties to be satisfied, right? And this is, I think, this is the prevailing approach in the literature, right? So basically, taking everything else and trying to convert it to approval ballots in all possible ways, like by considering all the different cutoffs, right? So that actually gives you some positive results, right? Kind of working with utilities or rankings directly, I think, is uglier, right? But kind of maybe more flexible.
Maybe one more question, the visionary question. What do you think the research of multi-winner election in 5 years or in the next few years? Research change.
Okay, so good question. Yeah, so I think I would sort of want it to move towards more representative, kind of more representative ballots, right? And maybe also kind of towards the incentives for the side that proposes the alternatives, right? So especially in participatory budgeting, what is super interesting to me is that if we have these different voting rules, but we also have the entities who propose the project for participatory budgeting, right? So what are the incentives to propose this or that project? How do they choose the scale of that project, whether to merge or split, right? And kind of to understand the whole ecosystem around participatory budgeting.
Thank you.
Thanks for the talk. So regarding your applications, how important is it actually to have very efficient algorithms? So is the P versus NP question here, does it actually matter, or are the numbers
Okay, so
too small?
depending on the specific application, right, and we can go through those. I mean, participatory budgeting, yes, it's okay to aggregate the ballots in 3 days, right, but maybe not much more than 3 days, right? And depending on the scale, right, so kind of just running PAV may not be feasible, right? So, or kind of the tweaks of method of equal share that actually take kind of a few hours to aggregate, kind of, which is okay. So okay for actual execution, maybe less okay if you want to experiment, right? So maybe kind of going back to what I was just saying, if proposers are trying to figure out what to propose, right, and want to play kind of experiment with several different scenarios, right? So for that kind of work, you need computational efficiency, right, or for any kind of analysis, right? So blockchain validators, right? So there, because this happens daily, right, and it needs to happen fast, right, and in some verifiable, either on chain or off chain, but in some verifiable way, right? So computational efficiency actually matters, right? So LLMs, yes, we absolutely want computational efficiency. Right, so depending on the applications, I would argue that for participatory budgeting specifically, kind of the case for computation efficiently is the weakest, but for blockchain and LLMs, I think it's there.
Okay, thank you.
You mentioned this example where there were 2 candidates that were approved by almost all voters, and then one other candidate that was approved by just a small set of voters. And you said that for justified representation, it would be okay to select this one of the very strongly approved candidates and then this other candidate. But this is not necessarily fair either. So are there applications where we want to select committees that cover as many voters as possible?
Oh, yeah, so kind of one example is, so my co-author Piotr Filashevsky has his favorite example, and this is choosing movies to be shown on a plane, or if you will, kind of ordering different flavors of pizza for a group meeting, right? So where it's probably kind of, more important that everyone, including vegans, including people with gluten intolerance, have something to eat than providing everyone like several varieties, right? Even if you have a lot of people who like pepperoni, right? So maybe it's not super important to have, pepperoni with vegetables versus pepperoni without vegetables than to provide something for those, 2 gluten-free people in your community, right? So sometimes you do want maximum coverage. Sometimes you want to maximize, well, utility, kind of the total number of approvals, right? But sometimes you care about proportionality, right? And it's kind of, yeah, so as a community, we are trying to sort of develop a set of guidelines, kind of when you should care about what.
2 short questions. So can you go back to the slide with the Thiele example in the second half of the talk? Yeah, can you go to the slide where you had this like hard instance for greedy set cover? Yeah, sorry, but I want to ask something about
Earlier or later?
the later one.
Here? No.
No, the Thiele one.
The Thiele one? Okay, no, so that would be before. So let me continue going back.
No, the previous one, where in the top right, there was this hard instance for set cover. Like essentially you had this one candidate C1, which was supported by three groups of, like both groups of people.
Mm-hmm.
And you had these candidates C2 and C3, which were supported by like disjoint groups of people.
Oh, yes, so let me go back to that example.
Yeah, exactly. So here, I understand that the correct PAV output would be C2 but C3. But when I think about it from a societal point of view, it's this kind of polarized choice in the sense that this candidate C2 is picked by one group, C3 is picked by another group, but C1 seems to be a much more agreeable candidate among different groups. So are there versions of this which take this into account to avoid such polarizing?
Thanks for asking this question, because I have a kind of new project. So we published the first paper in this series, right? But there's also follow-up where we exactly to do that, right? So when we try to build a committee that interconnects voters as much as possible, right? So this can also be kind of formulated in the language of covering, right? But yeah, so this is kind of something that is kind of the first paper on that. We published it in 25, AMAS 25, right? And the goal is to build a committee such that ideally kind of, so the desideratum we're trying to maximize is that for every pair of voters, there's a candidate that these two voters approve. So for every pair of voters, there's something that connects them, right? So that we avoid complete separation among the voters, right? And there are more sophisticated version of that, right? So this is kind of also computationally expensive, right? And it seems orthogonal to JR and kind of all the other desiderata I talked about, right? So this is kind of yet another axis in that space, right? But kind of to me, yeah, this is something that I want to think about. This, I think it's nice to have a committee that actually tries to, to show voters that, other people who differ from them still have something in common, that they agree on something with other people.
Yeah, then maybe another short question, which would be, so as you said, machine learning, people now turn to like fairness notions based on social choice. So they have some objective and the constraint is given by social choice. Do you think this will be a larger trend now? Or do you think that these social choice problems are essentially too hard, which kind of makes solving the constraints already so hard that the resulting optimization problem becomes infeasible?
It's interesting. So I'm now running a reading course kind of at Northwestern where we try to read papers kind of that use different social choice rules for AI alignment, right? And there's a bunch of them that appear in the literature, right? So reinforcement learning from human feedback in particular kind of implicitly aggregates according to very simple voting rules, but there's been kind of recent proposal that, implicitly or explicitly say, okay, let's use more sophisticated voting rules, right? And what I observed, at least in one case, kind of machine learning researchers with no social choice background reinvented a classic social choice rule, namely maximal lotteries, right? So I think kind of there's an understanding within the machine learning community, right? So not external, right? That sometimes kind of sophisticated aggregation methods are needed, right? So even if kind of this doesn't necessarily lead to axiomatic analysis, right? And in machine learning, they have, they have regularizers, they have approximation, they have things that make kind of theoretical axiomatic analysis difficult. I think the ideas from social choice kind of, liberally interpreted, not literally, but liberally interpreted, will be useful in machine learning and are increasingly adopted, right? And it's happening organically.
Thank you. Are there any further questions from the audience?
I'm curious, I guess if you could go one slide forward about the theorems.
Yeah, let me flash them all at you. Yes.
Even further, where you presented all the theorems. Yeah, so in particular, the last one to me seems weird because I guess utility vectors are, well, arbitrary numbers that we might assume people have, but we basically don't know. Because let's assume there's a tie in the vote. Having one extra candidate actually has a great utility for the voters because you would get the majority in that vote at that point. And even when there's like even two candidates, like getting the second one is extremely important because you get the totality of votes instead of splitted votes.
Right.
So assuming that it has to be the harmonic series, to me actually looks like a limitation of AVs instead of like an argument in favor.
So you're pushing back against the monotonicity assumption here, right? So, okay. So monotonicity assumption captures, so you're exactly right that we are selecting committees for different purposes, right? And if you're selecting committees, then that will later make decision by majority voting, right? So accept the argument that we don't necessarily want monotonicity, right? So in this context, I'm thinking of a committee as a talking body where different opinions are being heard, right? Or perhaps kind of ordering K pizzas, selecting K speakers where kind of two interesting talks are not twice as interesting as one interesting talk, right? So this is the sort of settings where you care about representation, right? But there won't be a subsequent majority voting stage, right? So yeah, so it kind of, so monotonicity assumption captures some uses of kind of multi-winner elections, not other uses. Right, I think your intuition comes from a different set of uses compared to what I had in mind, right? But yeah, so kind of going back to this. Okay, I mean this is a characterization result. It is what it is. So you can read it as a criticism of the axiom. You can read it as a criticism of voting rule, right? But kind of all it tells us that kind of you can't have both.
Yeah, and also the ones above seem a little bit strange because what would happen? I guess we said that they resemble greediness, but what would happen if we have extra seats, but we already covered everything?
So then you can, okay, so in practice, you expect to have, the straggler voters who like something that no one else likes, like voters who self-nominate themselves as candidate. So I think in practice, you'll be able to cover more and more voters as you go along, right? So if not, right, so if you already covered then the rule itself imposes no constraint on what you do next, right? And yeah, so you can select candidates arbitrarily, right? So the impossibility result does not hinge on that, right? So the impossibility result holds for any kind of breaking this, ties at the tail.
Okay, thank you.
Just concerning applications, you had on one slide that this Sweden has adopted kind of one of these algorithms. Are you aware of other countries, or you are now in the US? Are there discussions?
Okay, so we've been trying to talk to the guy who runs the Evanston participatory budgeting project, right? So this is in fact my colleague from Northwestern. So he's not a computer scientist, right? So he works in kind of information engineering, kind of that type of department, right? So we started talking to him, right? So his work in that space is orthogonal to, I mean, he's more interested in how projects get nominated and how people discuss them rather than kind of what is the final rule for selecting projects, right? So in principle, so he doesn't object to switching to a different rule, right? If we have argument that it might be a better outcome, right? So eventually we hope to flip the Evanston participatory budgeting process to using method of equal shares.
So I'm looking to the participants. Are there any questions online? Just ask. No questions online. Then I would like to thank you again for your presentation. Thank you for attending. And Professor Elkind is still here the next day. So if you have further questions or want to interact with her, please go ahead. Thank you.